Hi everyone. In this video, we will talk about the basic application of the Kirchhoff voltage law and Kirchhoff current law. The KVL and KCL, which is abbreviated for Kirchhoff voltage law and Kirchhoff current law, are essential to solve any electrical circuit. So this is very imperative to understand for the first year students or for the 11th and 12th students to understand that how to apply KVL and KCL for solving an electrical circuit. So let's begin. So before proceeding to KVL and KCL, it is essential to understand the distinct difference between a node and a branch. So here the first is this circuit simply shows that three branches, let's say I'm having three resistors connected in a similar fashion. So let's say this is branch number 1 of resistance R1. This is branch number 2 of resistance R2, and this is branch number 3 having the resistance of R3. So all these three resistors are meeting at this point. So this point is nothing but can be called as a node. Whereas if I'm having a single branch, let's say our resistance R1. So this is nothing but my single branch, and this can be further extended to having a series combination of R2. Similarly, again here we have three branches, branch 1, 2 and 3. So all these three are the individual branches. However, whether they are connected together, again this will be called as a node. So we always apply KCL at given node, or we have to take a node, whereas we always apply KVL in a given loop. So now let's understand that how and where we need to apply KCL, and how and where we need to apply the KVL. So let's quickly go through the definitions of KVL and the KCL. The KCL is nothing but the algebraic sum of all the currents entering at node in a circuit is equals to 0. So this we can understand simply by having, let's say I'm making a circuit over here. So again, taking the node where my three branches are meeting, let's take one more branch which is connected in this fashion. So now let's understand that this is one complete circuit. So here in this circuit, I have one voltage source which is given like this. So let's say this is V, and we have resistance connected in this fashion. So for this node, if I have to denote the numbering of the nodes, so I'll always start with a reference node which is always at the ground potential. And with respect to this reference node, this is my node. So this circuit, I can say that it is having one node with respect to the reference node. Here I can say that some of you or some of we can argue that this resistance R2 is meeting at this point, the second terminal of R2. Similarly, the second terminal of R4 branch is meeting at this point, and similarly the second terminal of R3 is meeting at this point, which is nothing but a similar point. So we can argue that this is again one of the node. Here we need to understand that all these second terminals of whether it's R2, R4 or R3, they all are meeting at this point. So the voltage difference or the potential of these nodes or potential of these points, secondary of R2, second terminal of R4, similarly second terminal of R3. All these 3 points are at the same potential, which we have considered as a reference point or at the ground level point. So with respect to this, we have denoted that this node will be of some other potential. So that's why we have given that this is node number 1. And as of now, we are not going to solve this circuit. We are just simply understanding the KCL. So let's say this current which is entering is I1. This current in R3 branch is I3. And similarly, this current is let's say I2, and this current is I4. So easily we can see that at node 1 we have 4 current which is either incoming or the outgoing from the node. So if we have to take that, what are the currents which is incoming towards my node, so I can easily see that the I1 is the incoming current. So let's say if I'm taking this I1 current as a positive, which is the current which is entering, so the other current which current are leaving to my node, I have to take with the different sign. So here we can also do the vice versa also. Either if the current is entering in the node, if I'm taking that current as negative, so the rest of the current which are leaving to my node, I have to take that current, all those are the positive. So vice versa is both are the true. So here if I'm taking the I1 is positive, which is incoming current, and I2 is outgoing, similarly I3 is outgoing, similarly I4 is outgoing. So all the three currents are negative, which is outgoing. So algebraic sum of all the 4 currents will be 0. So this is the meaning of the KCL in a circuit at a particular node. Similarly, for the KVL, the definition is that algebraic sum of all the voltages around any loop in a circuit is equals to 0. So this works on the voltage drop, the KVL, whereas the KCL works on the my current. So again, taking a simple example, that algebraic sum is nothing but, let's say if I'm having this kind of a circuit, a simple circuit having 2 parallel branches. So here, let's say this is V, again this is R1, R2 and R3. So I'm having 2 loops here. This is loop number 1. Similarly, this is loop number 2. So these are the 2 loops, and the third loop is, I can consider that the outer loop, which is this, the outer loop. That also is applicable for the KVL equation formation. However, these are the 2 inner loops where my R2 is sandwiched between loop number 1 and loop number 2. So here R2 is nothing but the sandwiched resistance which is between loop number 1 and loop number 2. So if I have to write the equation for loop number 1, so pay attention over here. I'm starting from here, which is I'm going in the clockwise direction for the loop number 1. So I'm starting from here, and let's say that I'm going from the lower potential to higher potential for the given voltage source. So when I'm going from the lower to higher, the voltage drop will always be positive. And when the current is entering in R1, so this current, let's say that loop 1 current has I1, loop 2 has current I2. So when the loop 1 current, which is I1, is entering in R1 like this, from here, because I have already chosen the direction of the I1, which is clockwise in loop number 1, which is shown by this arrow, right? So you can assume any direction, either clockwise or anti-clockwise, but once you have taken the assumption, and do not change, otherwise your all the equations will be incorrect. So here, once I have taken the direction, the I1 current is entering in R1 like this. So this point will be the positive when the current is entering to my R1, and this point will be negative in terms of the voltage drop. So when the current is leaving, it will be leave on the lower potential. When the current is entering, it will enter in at the higher potential. So when I'll apply the KVL in this loop number 1, so V, and when I'm going from higher to lower potential, so this voltage drop will be negative, and the voltage drop will be equals to the current which is going through the R1, which we have taken I1, and the resistance which is R1. This is as per the Ohm's law, V is equals to IR. Similarly, when I'm going in this direction, the R2 having the 2 currents, one I1 current which is coming from upward to downwards over here, and similarly the current I2 is coming from downwards to upward. Now, this we always need to remember that for the loop number 1, the current I1 which we have chosen, for that we always take that I1 is more than the other loop currents. So therefore, the voltage drop is always going to happen in this fashion, that I1 is more, so that's why plus, and this will be the minus. So here we can understand that this is nothing but the total current which is going through the R2, that is nothing but I1 minus I2, because I1 we have assumed that it is more than the I2, and into R2. So this is the equation, KVL equation for my loop number 1 is equals to 0. So sum of the algebraic sum of the voltage drop is equals to 0. So I hope we have understood the basics of the KVL and KCL. Now we can understand both the laws by taking one example. So this is a very simple example which we have considered here. For this red circuit, it can be easily seen that the current 6 ampere, which is I1, is something which is incoming. So this is nothing but the incoming current. So therefore I2 and I3 is leaving. So incoming current, which is 6 ampere, should be equals to the sum of the outgoing current, which is 4 plus 4 plus 2 ampere. So incoming current, total incoming current should be equals to the total outgoing current. So that in that way also we can see the KCL. Instead of saying that the algebraic sum of the total current entering or leaving at a given node is equals to 0, so that can be understood in other way, that the total incoming current should be equals to the total outgoing current. So for this circuit which is given over here, the incoming current is I5, I1, these two are the incoming current, and I4, I3 and I2 are the outgoing current. So we can say that I5, the sum of the I5 plus I1, which is the incoming current, equals to the total sum of the outgoing current, which is I4 plus I2 plus I3. Similarly, for this circuit, let's understand that if I need to apply the KVL in this loop and I'm going clockwise, so here again I'm starting from E1 and going from lower potential to higher potential. So this will become E1, and forget about these current values. Let's say for the loop current, I'm taking that my current is I, because here we have only one loop and I've considered that this loop current is I. So the loop current is also assumed, I have assumed the direction that my loop current I is flowing in the clockwise direction. So when this current I will enter R1 clockwise direction or in this fashion, so this will be the positive and this point will be the negative. When the current is leaving, then it will be of the lower potential. So my equation now becomes E1 minus I into R1. Similarly, when the current is entering R2, again this will be plus and this will be minus, and this again minus I R2. Similarly, when this is entering, this plus and minus I R3. And now we are going from higher potential to lower potential for E2, then this becomes minus of E2, and finally the current I is entering R4, so this become plus, this become minus, so this becomes minus of I into R4 is equals to 0. So this is equation when I'm considering the loop current. Similarly, the same thing, now we can consider that already the current for all the branches are given differently. So let's say the current is I1 over here, the current in this branch is I2, the current in this branch is I3, and current in this branch is I4. So if let's say the current directions are already given and we need to form a KVL equation. So as per this, Now let's say when I'm starting again from E1, so this becomes E1, and the current through R1 is going I1. Now we are taking the second case. So again R1 into I1. And when I'm moving in this direction, the current is I2, which is entering R2, and I'm also going in the same direction of the current direction. So my voltage drop again will be coming in the negative, which is R2 and I2. And now when I'm going in this direction, which is clockwise, I see that the I3 is opposite to my direction of the KVL equation. I'm applying the KVL equation and I'm going clockwise direction, whereas the current I3 is coming in the reverse direction. So in this case, when I3 is coming from downward to upward, the voltage drop which will be made against R3, with this is plus and minus. And I'm going opposite to this, so I'm entering from the lower potential and I'm then going towards the higher potential, which is positive, this one. So this voltage drop will be plus of R3 and I3, and again for the E2 I'm going from higher to lower, then this becomes minus of E2. The last again I'm going opposite to I4 over here. The similar fashion, the voltage drop across R4 will be coming positive, which is I4 into R4, and this is total is equals to 0. So therefore this and this equation both are same. Similarly, we have one more circuit over here, and here we have, instead of one loop, we have two loops where the R2 is being sandwiched between two loops. And if, let's say, I'm assuming that this loop current is I1 and this loop current is I2, so I'm going to solve this circuit with both the KVL and KCL quickly. So this is I1 and I2 I have taken, so I'm just writing two equations. For the loop number 1, I'm starting from E1, from higher to lower to higher potential, and the even value is 20 volt. So 20 minus 10 of I1, and minus for the R2, again I'm considering that I1 is more than the I2, so 4 into I1 minus I2 is equals to 0. So this is equation number 1 in loop number 1. Similarly, for the loop 2, I'm starting, let's say, 12 volt, again going in the clockwise direction, and for the 12 volt I'm going from low to higher potential, so this was 12 minus 8 of I2, and when I'm applying the KVL in loop number 2, so I'm considering, or I'm assuming, that I2 is more than the I1, so in that case minus of 4, instead of I1 minus I2, now we will have the I2 minus I1, and is equals to 0. So these are the two loop currents which we have formulated by considering the two loops. And this kind of analysis where we are finding the loop current and then the rest of the values, so this is nothing but is also known as the mesh analysis. So mesh analysis is nothing but an application of the KVL in the loops. Why we call it a mesh? Because something R2 here is being sandwiched or being meshed between the two loops. So therefore, this is nothing but the mesh analysis. Similarly, when I'm applying the KCL, again let's understand that at node A, I'm taking that this is my reference node. So the A is my reference node, and with respect to this A, this node C, I'm considering that this is one of my node at having a different potential. And forget about these branch currents, which is already denoted over here. We can formulate the KVL equation as per that also, but it is not necessary. So for the KCL, let's understand that I'm taking that the node C is at the voltage potential having the V. So V is the potential of the node C. So here I'm applying the KCL, and this becomes, for applying the KCL at this node, let's say this current is incoming. Assume any direction. I'm assuming that all the currents are outgoing. So instead of incoming, and it also becomes easy. Let's understand that all the currents from the node is outgoing, all the currents from all the branches. Why we are taking this? Because the current will be outgoing only when the node C is at the higher potential with the other nodes. So this gives me a very simple explanation over here. So here, applying the KCL at this, first the current which is going this one, and this is V, the potential of the C node, minus of 20 volt. So V minus 20, because we are going for this branch here. So the voltage or the potential of the node C, which is V, and here we have the potential of 20. So the total potential difference between C and A node in this branch is V minus 20. So V minus 20 is the total voltage or the voltage difference of this branch, and divided by the resistance. So V divided by R is nothing but my current I as per the Ohm's law. So this is outgoing. Other two currents are have taken the outgoing. So for this branch again V, and the reference node we always take that it is the zero potential. So V minus 0 is nothing but V, and divided by the resistance, which is 4. And similarly the other, and this becomes the V plus 12 volt. So V plus 12 volt, because this having the opposite polarity, so this is V and plus 12 volt, and divided by 8. So all the three currents we have considered outgoing, so all three currents will be get summed, and that is equals to 0. So if I need to, so here with respect to the KCL, I have one equation where I find the voltage V. So once I find the voltage V, I can find out the current in any branch easily. Like this current, this branch current, which is this one, is nothing but V minus 20 divided by 10. Similarly, this branch current is nothing but V divided by 4. So once I get the value of the V, I can find the value of any branch current. Similarly, with the help of the KVL also, I can find out the I1 and I2 and the rest of the current by solving these two equations. So I hope we have understand the basic application of the KVL and KCL. And further going, we will take the few different examples of the circuits, and by doing the practice we will understand that where it is easy to apply the KCL or where it is easy to apply KVL. It is not about the difficulty, rather it is about the simplicity. For this circuit also, we can see that for the KCL we only need to solve one equation, and once we get the value of V, we can find out the rest of the value. Similarly, if I'm going with the mesh analysis or the application of the KVL, we need to do the lot more computational effort. So with this, again we are going to take the theorems and then the most of the critical examples where we will understand that how to apply KVL and KCL, and we'll do some practice. Thank you. Thanks a lot.